Any question? Okay. Can I get? If you remember, yesterday I talked about the function, and I said that for a real variable x and y, multivariable calculus, x and y are independent. Therefore, you can write a function f of x and y. But in the complex plane, for the complex variables, if I say that this is a function of z, then it is a function of a unique combination of x and y, which is x plus iota y. So what is the significance when I say it is a function of x plus iota y? Can we say that it has some relation with the analyticity of a function? I mean, if we look at the function, by just looking at the function, can we say that it is an analytic function or not? And if it is an analytic function, if we map it from one plane to the other plane, and is it possible to find certain relations? And if those relations hold, then we can say that that function is an analytic function. Then these relations are known as the Cauchy-Riemann conditions. So today we actually find these relations in this lecture, which are the Cauchy-Riemann relations. And then suppose we get a function which is analytic. Its derivative exists. I'll talk about what do we mean by the derivative in the complex case. Can we say that it has a derivative in the whole plane for which z is less than infinity? If the function obeys this kind of a property, then what kind of the functions we have in this case? This is basically the content of today's lecture. So let me briefly explain you. Suppose you have a let me talk about the derivative. You know, Pravesab just talked about the derivative at a point. He said that it doesn't matter whether you approach from to that point from bottom, top, right, left. That should be uniquely defined, right? So, for example, if there is a function of real variable x, and I have to find a derivative df over dx at any point. We know that how we can do it. We can just do it. We can take a small change in x, and then we can write f of x divided by the delta x. It's fine, right? The only thing is we have to change delta x to be 0. Right? So suppose you have some curve and we have to find the derivative around this point. I can call this point to be x naught, whatever you like. So it means I have to find x naught plus delta x minus f of x naught over this. So this usually write df over dx at x is equal to x naught then. And x naught is this point. No, I can approach from this side to this point, or I can approach from this side to this point. It means that this equation remains the same if I say I approach delta x from negative side. I call this a negative side to this way, from left side to right, and I have f of x plus delta x minus f of x over delta x. It is same as f of x plus delta x minus f of x over delta x if I approach and limit delta x approaches to 0 from positive side. It means that the function is perfectly uniquely defined. At least this is for first derivative. This is my rule of thumb now. Do you remember? For a complex number, we have a problem. And the problem is the following. When I say, you remember what is a complex? Let me define the complex function first. Suppose you have a z plane. When I say z plane, it means in this plane you have x and y. Iota y I can write because this is I can also write x as a real axis of z and y as an imaginary axis of z. I can make a change, I can define a function, then this becomes the domain of a function and this becomes the range of a function. I can uniquely map this to this plane. Let me call it in a RFK language, this is a W plane. Now the Z plane function can map that to W plane, and you can write any combination of X and Y. The whole idea is that both Z and W, they are in the complex plane. They belongs to this set of complex numbers, complex variables. So how I can write that basically? You know Z is X plus iota Y, right? So I can write f of Z, as I said, which is something like u of x and y, where u, x, y is a function of real variables x and y. So u is real, just like here x is a real, plus iota v x and y. In our yesterday's language, if you remember, if this is an ordered pair of x and y, then this is an ordered pair of u and v. And u is some function of x and y, v is some function of x and y. Now, how to find this function of x and y? Let me consider a very small, very simple case of f of z. Let's take it as a z cube. Suppose I give you a function f of z, which is equal to z cube. It means that you can write it as x plus iota y cube. Yesterday we opened this thing, if you remember. So this is equal to x cube minus 3x y squared plus iota, and then we have 3x squared y minus y cube, right? So z is in this plane, this function map that to w plane. In w plane we have u and v. It means I can write this is equal to u of xy plus iota v of xy. Is fine? Everything is correct? Okay, so as I told you that if you have two complex numbers, you have to compare. On one side you have a complex number, on other side you have to complex number. Both are equal. It means the real part is equal to the real part on one side. The real part of one side is equal to the real part on other side, and same is with the imaginary part. So this implies is you have u of x and y is equal to x cube minus 3x y squared. So you see, in terms of the variables of this plane, you have calculated the functions that lies in the w plane. And similarly, you can write v of xy as, just ignore the iota because we are comparing the imaginary part, and this is x squared y minus y cube. Is fine? So for any sort of a function, if you are not giving u and v, then you can calculate u and v from this equation, or you can find whatever you like, you can say. So once I know u and v, and you know that u and v are the function of x and y, the whole problem is what happens if I change x? Z will change, definitely, because z depends upon x. If I change y, z will change. If I change both, then z will definitely, you will look that it will definitely change, that x goes to x plus delta x and y goes to delta y plus delta y. It means for a z, I can write exactly this kind of a definition as far as I am living in this plane, and I can say that, okay, you can put delta z is equal to 0. Let me give you a very simple way of definition in this case. Okay. Suppose you are given f of z is equal to z squared or z cube, whatever you like. So suppose I have f of z Now this is the simplest function, f of z is z squared. You are just taking delta z goes to 0 because irrespective of x and y, I'm not expressing it in terms of x and y. And then I'll express it in terms of x and y and I'll show you what is the problem in that case. So I can write exactly the definition that, okay, df by dz, I can calculate from this one limit delta z goes to 0 until and I know that delta z is my parameter on this curve. So I can change, and then I can write f of z plus delta z minus f of z over delta z. Around any point you can find z naught. So I'm finding it around point z. So then we can write limit delta z approaches to 0. What is my, so let me first calculate f of z plus delta z. So what is f of z plus delta z? So, sorry, this is equal to z squared plus 2z delta z plus delta z squared, right? And I can calculate f of z also, which is equal to z squared. And if I take the difference of the two, so if I take the difference, this is gone. So it means f of z plus delta z minus f of z over delta z. I am dividing with delta z also. I can take a delta z common from here, and then I can write 2z plus delta z over delta z. So one delta z is gone. Now let me take the limit on both sides. I am taking this limit on both sides because of not enough space I have written it over here. So now I can put delta z is equal to 0. So then you have 2z. It's perfectly fine, just like the power law. Just like the real variable, you have written it is a d by dx of x to the power n is n x to the power n minus 1. In our case, n is equal to 2. So this means I can generalize it that if f of z is equal to z to the power n, then df by dz is n z to the power n minus 1. No problem at all. But I haven't expressed z in terms of x and y. Now let's suppose a simplest z, which is different from x plus iota y, because z can be any complex function, right? It can be any complex variable. You can have x plus iota y, you can have x squared plus iota y squared, whatever you like. So let me take a very, very simple case. And then you run into the problem. Let me take f of z is equal to y plus iota x. Instead of x plus iota y, let me have y plus iota x. Now what? Any suggestion how to do its differentiation? Because now z is not ordinary z. Yes, please.
It's just equal to iz.
Okay.
This was the it's equal to or minus like that.
Okay.
I think there's some relation, though we could represent this in terms.
Okay. So first of all, you remember what is over z? Z is x plus iota y. If I change x to delta x, I change y to delta y. It means I can change delta z. I can write as delta x plus iota delta y. It's fine. Small change in x, small change in y. I have a small change in delta z. Now if you calculate f of z plus delta z in this case, then you can see this one. Exactly, y plus delta y plus iota x plus. Here the life was very simple because f of z is just the z. But here f of z is not equal to z. It is some different function of x and y. So, is it fine, right? Now, if I write f of z, then I have y plus iota x. Now, let me take the difference of the two. What will happen then? So, on the left hand side, I have f of z plus delta z minus f of z, whereas on the right hand side I have this y is gone, iota x is gone, so I have delta y plus iota delta x. Is correct? Okay, so now if I divide it with delta z on both sides, and you remember delta z is what? Then you have delta y plus iota delta x over delta x plus iota delta y. It's very simple. Oh, delta y plus, this is fine. No, delta z is my delta x plus iota delta y. Z is my this one. This is a function of z. This is not z. Z is this one, x plus iota y. This is a function. Okay, so this is a complex number in my W plane. If you ask me what is uxy, I will say it is y. If you ask me vxy, I will say it is equal to x. So, okay, so thanks for asking. Let me clarify this. This is my u and this is my v in the W plane. But because I'm not going into the W plane, so there is no problem. Now there are the possibilities. Just look at this function in a plane. This is my real of z, which is x, and this is my y, which is imaginary of complex variable z. When I say complex variable z, I mean x plus iota y. When I say f of z, it can be anything. So, suppose you are at this point, and you can approach to this point from this side, you can approach to this point from this side, you can approach to this point from this side. I will clarify this when I use the polar coordinates. It will become very elegant then. But let's first understand for the simple xy coordinates. So now if I say delta z is equal to 0, it is not a binding that I have to go either from left or from top. I can go from any side because in this delta z lies in this complex plane, and I can approach to this point from any side I like. Let me take a very simple choice. The simplest choice is if I approach from along the real axis, it means my y is fixed, right? So my first choice is, so choice 1 is, I can take delta y is equal to 0. It means I have fixed this point on, I can just make a change along x-axis, y is fixed. And I can take delta x approaches to 0. Because if I do this with this choice, then once again I have my limit delta z goes to 0. Right? So if I use now limit for this one, for limit delta z goes to 0, f of z plus delta z minus f of z over delta z. Then you have, this limit will go to like this one, my limit is now delta x approaches to 0, right? Because I have forced delta y is equal to 0. I have forced it. Now you can do it like this one that, okay, so delta y is 0, so I have iota delta x over delta x. This is gone, so this is equal to iota. So from my first choice, df by dz around any point, if I call it as a z naught, you can say whatever you like, or z naught, or z whatever it is iota. It's clear? What happens if I choose I can also do it like this one. I can fix the point on x-axis, x-axis, and then approach along the y-axis to this point from upside or downside, doesn't matter. So I can use delta x is equal to 0, and I can choose delta y approaches to 0, because in this limit once again delta z goes to 0. So this df by dz then becomes what? So you have delta x is equal to 0, delta x is equal to 0, so you have delta y over iota delta y, which is equal to 1 over iota. And if you remember, I told you 1 over iota is the multiplicative inverse of iota. So whenever you have a complex number downstairs, you can just rationalize it. You can multiply its conjugate upstairs and downstairs, and then you can write it as minus iota. So df by dz from our choice 1 is not equal to df over dz from our choice 2, right? So it means if I approach delta z from anywhere, delta z goes to 0, and I have just selected x and y, not any other array. I can choose any other array also. I'll come to this point, because you can write it like this one. If you have delta x plus iota delta y, then you can, if you take delta x to be common, I will come to this point during the second half of this lecture, then this is just like a slope. So if you choose y is equal to mx, then you have this array. Depending upon the slope, you can define all the lines. So it means if you have a dependent on the slope, then you can say that, okay, the derivative is not uniquely defined, right?
So when we delta y and delta x, we said previously that x and y can be written as sine and cosine. We say that this is delta x 1 plus I tan.
I'll come to this sine and cosine business. Then when I put everything in polar coordinates, then I'll come to this thing. For the time being, I'm only in x and y. You can say that your R2 plane with y goes to iota y. So complex plane. It's fine, right? So you can see that it's not necessary that for a complex function you have the derivative approaching from any side to be the same. It means these functions are not analytic then, right? And even in your basic calculus yesterday, if you remember, we talked about this function f x dot, and if you take derivative from x side, you can approach, you have 1 on the other side, and then there is a corner, and at the corner there is no well-defined df by dx. So you can say that that's kind of a abrupt change. So whenever you have an abrupt change, it is not a continuous or smooth function. Yes. First, sorry.
Sir, is there like even in this function?
Yes, please.
Is there like a domain where it is analytic?
I'll come to this point.
Okay.
Because domain, and that is one of the most important aspect in the complex variable. Sometimes we have, suppose you have 1 over z, 1 over x. You can say that, okay, it is finite for any value of x, but not 0. So it means whenever I define I can write this function, I will write the condition that it is not well defined at x is equal to 0. What kind of these x is equal to 0 singularities corresponds to in complex variables, that is a whole new subject, and that is why this is now known as the calculus of residues. We can just see the relation of 1 over z type term with the residue. But this is a very, very good question, but way advancement too. I will see that rational fractions are not analytic. I'll come to this point here. Hamna, please.
So for the derivative of the whole thing to exist, the limit as you approach it from any side should be equal.
Equal, yes.
So in this case,
it is not. So I can say that f of z is not an analytic function.
So we are defining analyticity,
Analyticity, you can say, yeah.
Yeah, to so the definition of analyticity
Is the, yeah, no
whatever
problem, yeah, no problem.
is that the derivative, as you approach it from any
Should be
side,
very smooth,
yeah, the function should be well behaved and
smooth.
smooth.
I'll derive all these
Okay.
conditions. You remember I wrote this x, u of x and y. I haven't said anything about the derivatives of u of x and y. So that's a very pertinent question. So instead of doing all these marathon again and again, why don't we find certain conditions? Because after all, my y was u in this case, my x was v in this case. Why not define certain relations of u and v that if those relations hold, we can say that that function is an analytic function. If those relations don't hold, then we can say that, okay, this is not an analytic function. This, let me now find out these relations. So if you have any question till this point, you can ask. And by the way, I will use exactly this terminology, the two choices. Delta y goes to 0, delta x goes to 0, and I'll prove conversely also that if this hold, then the derivative exists. So that you have everything kind of unnecessary and sufficient then. Question from backbenchers. You can speak, I can run with mic, no problem. Okay, so let me then write delta f in terms of u and v. So you remember I have written f of z as u of x and y plus iota v x and y. And let me use this shorthand notation. I can just write, it is understood that it is a function of u and v, because I have to save time in writing x and y all the time. So if I write delta f, I can say that it is equal to delta u plus iota delta v. There is no problem. I know u is a function of x and y. And if I have to change u, I have to change x to delta x, y to delta y. It means I have the partial derivatives with respect to x and partial derivative with respect to y. And what is my delta z? My delta z is delta x plus iota delta y. Correct? Why not find delta f over delta z in the limit delta z goes to 0? I can write it as limit delta z goes to 0, delta u plus iota delta v over delta x plus iota delta y. Any question till this point? This is my by definition is. I have a bad habit of not writing df by dz at a particular point, z not, no problem. I know at any point. Yes, non-singular point. Okay, so once again your choice 1. For delta z approaches to 0. What is your first choice then? Delta x goes to 0, okay. And then? Okay, first choice was delta y is equal to 0 and delta x approaches to 0. It means you have df over dz, this is equal to limit delta x approaches to 0. And then I have delta u plus iota delta v, but you remember delta y is 0, so I can write it as, because after all this is a small change, so I can just write it like this one. And you remember, if you approach to point close and close, because u is not a function of x only, Therefore, I have to use partial derivative because it is explicit function of x. So I can write it as partial f over partial u over partial x plus iota partial v over partial x. Right? Let's use the choice 2. The choice 2 for which delta z is equal to 0 is delta x is 0 and delta y approaches to 0. So I can write df over dz. By the way, when I speak, I frequently use this as du by dx, but I will always write partial u by partial x, right? So that's why I'll try to say partial, right? So this is equal to df by dz is now, you have to help me to write it. Yes, please. Delta z approaches to 0. Sorry. 0 हो जाए तो फिर तो infinity. Thank you. So limit delta x, delta y goes to 0, and I have delta u plus iota delta v over iota delta y, and I have iota delta y. Now, if I have delta y approaches to 0, this is iota, so this will go upstairs, so I can have minus partial u minus iota times, this is very important, partial y plus partial v over partial y. But because I am supposing that my f of z is an analytic function, right? The both choices will give me the same result, right? Sometimes we call it as an f of z to be analytic, or in some book we call it as holomorphic. Mathematics books usually write this word, holomorphic functions. I'll mention the name of the book at the end, which I followed for some portion of this lecture and of yesterday's lecture. In the yesterday's lecture, you can say. So it means this is, why not I write it as a choice 2 and I can write it as a choice 1. So it means the left hand side and the right hand sides, they should match with each other, they should be equal, right? So I can write partial u over partial x plus iota partial v over partial x. Then I have minus iota partial u over partial y plus partial v over. You have seen one very important thing that you have, I was expecting that someone will ask, definitely. These u and v have non-zero partial derivatives, right? And they're continuous. So it means, once again, you have to compare real part with the real and the imaginary part with the imaginary part. So you can write, so a real part will give you partial u over partial x is equal to partial v over partial y. Right? And then second is iota is gone, so partial v over partial x is equal to minus partial u over partial y. So if u and v obey these relations, then we can say that the corresponding mapping, the function, is an analytic function. These relations are known as Cauchy-Riemann. Sometimes we'll call them the Cauchy-Riemann conditions. And if these conditions, Cauchy-Riemann conditions for the functions to be analytic. So if these conditions hold, the function is definitely analytic. Now you try what you have done 15 minutes before. You remember your u was what? Please. कुछ गलत लिख दिया मैंने? This is compared with this double arrow compared with this. Minus इधर लगा दे. You can always multiply on both sides the same things. So you can write dv by dx is minus du by dy. It's fine, I guess. It's correct. You can see. No, there are the chances that something is wrong, so you can see. Okay. So you remember what was your u in last when I wrote f of z is equal to y plus iota x. Your u is y and your v is x. No, let's call this relation as a Cauchy relation 1 and this relation as a Cauchy relation 2. You can just put u and v in this way. So you can see that the relation 1 gives, if you take du by dx, it is 0, and if you take dv by dy, it is equal to 0. So condition 1 is fine, there is no problem with this. And then if you have the second condition, which is dv by dx, it is equal to what? dv by dx is 1 and du by dy is also equal to 1. But they should be equal with the negative sign, you know. But therefore the second condition, the second Cauchy relation, our condition is violated. Therefore this is not an analytic function. So you see, what we have done is we have translated the language of expressing function and then putting delta x goes to 0, delta y is equal to 0. We have found some relationship between the functions in the w plane. And what was the w plane? That was the mapping of the z plane, which are uniquely defined, you know, because these are the functions. So, any question?
So do either of the conditions respectively imply something about the function?
I'll come to this point, you know. So okay, so what happens if I take the y derivative of it and x derivative of it? Then perhaps I can make a pair of the two, you know. Right? So I'm not sure if they are the conjugate in some sense of each other. I'll come to this point.
No, I mean like for the function w, or sorry, u and v, they imply something respectively, like this condition shows this thing about the function and this condition shows this thing.
These are two conditions. You cannot isolate them. They have to exist simultaneously, you know. You have seen that this condition holds, but this doesn't. For any function to be analytic or homomorphic, whatever word you like, you can say, these two relations should hold simultaneously.
ये दोनों जो हैं ये अलग-अलग
कोई बात नहीं बता रहे
नहीं.
फंक्शन के बारे में.
Okay, so how about, let me make a claim and then you can justify that claim. And that claims come with the discussion that we have done yesterday. You remember yesterday I said that f of z is a function which is independent, z is independent of z star. So if I say that f of z is a function of x plus iota y unique combination, it can never be function of x minus iota y. So it means that if f of z is an analytic function, what do you think about the f of z star? My claim is the following, and you can justify this one, that partial f over partial z star should be equal to 0 for any function to be analytic. Instead of going to a very lengthy, tedious calculation, just check if your function involves z star. Just check if your function involves z star explicitly. Why not try this thing? F of z is equal to z star, which is x minus iota y. You can just put these Cauchy relations. You have du by dx, and then you have dv by dy minus iota. And then you can do the other one. And you will see that Cauchy-Riemann conditions, they are violated. See, if you can check it rigorously for many functions, you know. Why not? You can check it was, you know, this definition is very simple in my case. If you go to the polar coordinates, what happens? What will happen then? You know your r is what in polar coordinates? X squared plus y squared, right. And if you write it as, then you can write it as a z and z star. You can check this thing. This is not an analytic function. According to my definition, this involves z star, and any function that involves z star is not analytic. You can just check it with Cauchy-Riemann conditions.
We would have to do all of this for this as well.
You know, I'm saying that why not I make a claim and then I can justify it for some functions. It has no explicit dependence on z star because z and z star are my two independent functions. You can try it for as many functions as you like. You can do it like this one. For example, your z star, okay, you can just write, what is u?
Y minus iota x, the state will be y minus iota x.
No, I'm saying this is z star. F of z is equal to z star, which is x minus iota y. So u is x, v is minus y. First condition fails. No need to do all these exercises again and again.
But how is it making it easier? I mean, if you
I'm saying that z and z star are independent.
okay, so you are proving that.
No, I'm claiming that. I'm saying that my claim is justified with this thing. Yesterday I told you that f of z is a function of a unique combination of x and y, which is x plus iota y, and not of x minus iota y. So it means the function which is a function of x minus iota y is independent of the function which is a function of x plus iota y. And if something is independent, then partial derivative of that is 0. If you're,
Okay,
yeah,
I get it.
you got it, right? Partial, not total, partial derivative, not an explicit function of z star.
If we had a complex mindset,
Let's make a rule, everything is complex here.
if we take a more complex function,
Okay, sure.
complex looking function,
Okay.
if f of z was say y square x something,
Anything,
the
yeah.
thing that you chose for z cube, I cannot see what you're trying to say with this
Okay.
equation.
Do you think z cube involves z star?
What
No.
is z? Z star is
Z
just
star
this.
is x minus iota y.
But,
Z is the combination which is x plus iota y. Let me say one thing. Z star is combination which is x minus iota y. This can help you to write x as z plus z star over 2, and this can help you
Okay.
to write z minus z star over 2 iota. So you can see that you have written two independent coordinates as two independent functions, you can say as a two independent functions, z and z star, x and y. So I'm saying that if any function involves z star, it is not an analytic function.
okay.
You can, by the way, what about x? X has no y, but it involves z star, you can see. There's no need to check all these conditions. So for the functions for which I can write in simple expressions in terms of z and z stars, I will always prefer to check this partial derivative with respect to z star. If it is not equal to 0, without any hesitation I can say that, okay, this
It
function
is
is
analytic.
not analytic.
Not analytic.
If it is,
I think I would have to do some examples to like
Yeah, sure,
actually
sure.
see.
okay, you can
what
do
is going on
like
here.
this one. What is df by dz star? Half. Not equal to 0.
Yeah.
Therefore, the function is not analytic.
Okay.
Right? So if any function involves this thing, okay, so this holds, then the function is, if this holds, then function is analytic.
Okay.
So whenever right hand side is non-zero, you can say that, okay, function is not analytic function. Right? Okay, so how about, okay, so you have seen that R is z star. How about theta? How about theta? Tangent inverse y over x, quite complicated, right? So we know that z is equal to r e to the power iota theta, right? So you can also write z star, which is equal to r e to the power minus iota theta. And you remember r and theta both are real functions. And then what you do? You can just take the ratio of the two. This becomes e to the power iota 2 iota theta. Or you can say theta is 1 over 2 iota and then log of z over. Does it involve z star? Tangent is very annoying function, because it has sine over cosine, and when cosine becomes 0, it goes to infinity. But this looks quite much simpler than z over z star, even though it is a logarithmic function. But you can say, okay, so I have a bad habit because when I write this one, it's very difficult to understand because of my writing. So I always use log. Anyways, so you can say that this involves z star. You can see that, okay, df over dz star is not equal to 0. It means your theta is not an analytic function also. So you see, life is very simple. Instead of you have to write tangent theta is equal to y over x, y is equal to x tangent theta, and then you have to differentiate, and then you have to do everything. I think that life is very complicated. Here the life is very simple. Now I have a very small assignment for you because you have a weekend in between my lecture. So and by the way, that is a very good exercise. Can you derive these Cauchy-Riemann relations in polar coordinates? That's a very good exercise because sometimes you work in polar coordinates and life is easier in the electrodynamics, and in some cases you work in the Cartesian coordinates. So whenever you have to look at some certain kind of asymmetries, you will always try to go to this circular, or you can say polar coordinates, that at least you have a whole mapping of theta at a constant radius, for example. Then can you derive these conditions? You have to write r of r and theta, and then you have to define another function. You can call it as a theta, which is a function of r and theta, and then you can derive all the Cauchy relations and verify if the result is this one. I have tried to derive it, and I'll be happy to be proven wrong, but dimensionally this seems to be fine. So if my a theta is a function of r and theta, and the other is r, which is a function of r and theta, I can write it as a capital theta, but the problem is that it is very difficult to distinguish my capital bigger theta from smaller theta. So you can just verify that you have dr over dr is equal to capital R over r, and then partial of a theta over partial theta, and then you can derive the other also. But I have just given you one relation, so at least you can verify this one, and then the second relation will be fine. So if you have any question, then till this point. By the way, it's not difficult to let me say what next I have to ask. I'm too bad at this one, so I hope everything is fine till this point, right? All right, good. By the way, this r theta is kind of a length also for small theta. So this is how I remember derivatives when you go from one coordinate system to other coordinate systems. The d by dr is a dimension of length. R d theta has a dimension of length. So you can see that it is dA over dr theta. You can take r because this is a partial derivative. So in this way you can remember. If you have phi, then you have to write r sine theta outside. And if you have another, then you can do it like, you can generalize this. रट्टा लगाने का तरीका है. I have to justify one more thing before moving forward, and that is, I told you that this thing, I have proven that if delta z goes to 0, that is independent of the choice if the function is analytic. This you can do in a more fancy way also, that if the partial derivatives exist, you can just write it like this one, and let me do it very quickly, even though it is given in more or less all the books, but there is only one point which I would like to mention at this point is, if you write delta f, this is equal to du by dx plus iota right. So what I have done is use a function of x and y. So first I change x to x plus delta x, I change to y plus delta y. It means f changed to z plus delta z. And I can write delta f is like this one. So if I write delta f over delta z, then this is what? I can take delta x to be common from upstairs. So I can write partial u over partial x plus iota partial v over partial y plus partial u over partial y plus iota partial v over partial y, and then you have, I haven't said anything about u and v for the time being. So, and then I have, if I take delta x to be common, then I have at least my this choice is no, because even if I now take delta x goes to 0, it becomes a slope. Iota, very important factor. Thank you, Azhar. Right, it's fine. What happens if I can just cancel this delta y over delta x? Because you remember, if I take a straight line, then I can write delta y is equal to m times delta x plus some constant, whatever you say. And my delta y over delta x, then, if I take the intercept to be 0, it is slope. So this depends upon on which direction I am approaching to the point where I am calculating the derivative. Because it is the slope of a line that changes. Along x-axis it is 0, along y-axis it is infinity. At any other point it is in between any value. So this has a choice. This is a choice dependent. So it means that in this way, this delta f over delta z, I can't say anything about it. But if this is an analytic function, then Cauchy-Riemann conditions are satisfied. It means I can put Cauchy-Riemann conditions that for this one, what is delta u over delta y? Let's write these Cauchy-Riemann conditions then. So let me write du by dx plus iota dv by dx plus, what is du by dy? Minus partial v by partial x. And what is the other one? dv by dy? Partial u by? And then I have it's fine, right? This is, by the way, y. Now what you can do, if you take iota to be common from this one, okay, let's see how it goes. Let me take delta u over delta x to be common. This one. So du over dx. What I have in the bracket then? I have 1 plus iota delta y over delta x. 1 plus iota delta y over delta x. And if I take iota to be common from here, then dv by dx, iota dv by dx, then plus iota, then what? This one is common, so I have 1, and it has no iota, it has a minus sign, so when I take iota to be common, I have to multiply this with minus iota. So this becomes then 1 plus iota. So you see, if Cauchy-Riemann conditions hold, then the function has the continuous derivatives of u and v, du by dx plus iota dv by dx. So partial derivatives exist. It has no dependence on x, on which line you are approaching to delta set. So I have 3 rules. The partial derivative should exist, they should be continuous, and the Cauchy-Riemann condition should hold in order to have any function to be an analytic function. So these are the 3 rules. Let me repeat, partial derivatives exist, they should be continuous, and Cauchy-Riemann relations or conditions hold. If these 3 conditions are satisfied for any function of a complex variable, then that function is an analytic function.
With the Cauchy-Riemann conditions, weren't we trying to check the same thing?
Exactly.
So with this
No, you
third,
see, no, I said that I have tried to remove this delta y over delta x dependence because they were implicated by the Cauchy-Riemann conditions. That in which direction you approach doesn't matter.
what extra information are we getting from this new
At least
condition?
you have, if they are independent, then the partial derivative should exist. du by
So
dx.
in the first case, were we trying to check the existence of the derivative in the vicinity of some point? And in this case, is it the case that we are trying to check it for the entire function?
Okay, so you can say it like this one. If we have a function,
Yeah.
partial derivatives exist, and the Cauchy-Riemann conditions are satisfied, then the derivative will exist. This
But
has a
then
derivative of
for
various-
you use the Cauchy-Riemann conditions here.
Yes, unless and until I don't use the Cauchy-Riemann condition, my derivative depends upon which direction I am approaching. And then I can't say that the derivative exists because if the first derivative exists, it should be independent of the choice of approach. Whether you are approaching from right side, whether you are approaching from left side.
So for in deriving the Cauchy-Riemann
Exactly.
conditions,
Yeah.
we were approaching from the left
Any
and
side.
right of
Any
x.
side, any side, any side. This I have proved. You know, that is why delta f by delta y by delta x is m. M is a slope, so it can be anything. It can 0 to infinity. Yeah.
Okay.
You see, that's why you said that if I have used the Cauchy-Riemann conditions, there is no y or x slope dependence over here.
Okay.
So then this is a unique derivative.
But then when we had the Cauchy-Riemann conditions and we checked it for a function f, we said that it is analytic
function.
if
That
they
is the
hold.
requirement of an analytic function.
But now we are saying that this should also.
No, this is the implication of
Okay,
the
this is the
Cauchy-Riemann.
implication.
Exactly.
I thought this is the third.
No, I
okay.
told you that unless and until I use the Cauchy-Riemann conditions, I cannot remove the dependence upon y over x.
So with this, we are trying to check
Exactly.
partial u over partial x and partial v over
Exactly.
partial.
So you see what I said. If the partial derivatives of u and v exist
yeah.
with respect to x and y in xy plane or r theta in polar coordinates, number one, they are continuous second condition, and the Cauchy-Riemann conditions hold. If these things are satisfied, these 3 steps are satisfied, then that function is an analytic function.
But we could just check the Cauchy-Riemann conditions and say that
exactly. But we have to,
okay.
get a confidence that okay, if Cauchy-Riemann conditions are satisfied, then the derivative of the function exists. It's
Okay.
vice versa. If the derivative of the function exists, Cauchy-Riemann conditions must be satisfied.
So I can just check instead of checking the Cauchy-Riemann conditions, I can also.
I have just checked the implications of Cauchy-Riemann
Okay.
condition. If and only if this is a statement.
So I can verify the implication, and if
Exactly.
that holds, then I don't have
Exactly.
to
So-
check the Cauchy-Riemann
Exactly. So you can say that
conditions.
it's an if and only if condition.
Okay.
In my case.
It makes sense.
So if the derivative of function will, the function will be analytic if and only if the Cauchy-Riemann conditions are satisfied and the partial derivatives exist. Ouch. Yeah, please.
So what we would like for an analytic function is that we should be able to approach from any direction, okay? But you see the derivation of Cauchy-Riemann's conditions, we approach along the axis, either
Two
x
choices
or
only.
y. So we don't approach from any other. So they don't, if you only have those conditions, at that moment you don't know, I mean, if other directions are okay or not. So here you approach from any generic direction and use that information as well, and then you get some other conditions, and then you are sure that okay, now you can approach from any direction and the function would have a derivative.
Absolutely.
Yes, so
Yeah.
he just told you that.
Three
So
conditions.
you need to have those partial derivatives as well.
And that they should be continuous.
Yeah.
And just to entertain you, I will solve it in a polar coordinates. And remember, I'm giving you kind of a hint that if you move on a circle of a fixed radius, only theta will change. And if I make df by dz, you can say, and if this theta dependence is gone, e to the power iota theta is cancelled to e to the power minus iota theta, which is kind of a phase, then it means that I have no direction dependence, right? If that holds, then I can say that, okay, the Cauchy-Riemann conditions are satisfied again. So I'll come to this point. Thank you very much, yes, and that was most relevant comment, rather clarification. So now let me, someone asked me the question, that what are the implications of these Cauchy-Riemann conditions. So I have to remember them, somehow. I have du by dx and I have du by dy. So this is equal to dv by dx and this is equal to, no, it's not right. This is y and this is x. Let me see if it's correct, right? Okay. So what happens if I take the derivative with respect to y for this one? So I can write d2u by dy dx. Doesn't matter. X and y are independent, so whether you take dx first and dy later, or you can take dy first and dx second, no problem. So I have this is equal to d2 v over dy squared, right? What happens if I do the same over here? So I have to take a derivative with respect to x. So I have d2u by dx dy, and this thing is equal to minus d2v by dx squared. Correct? Now you can say that we can, because this is as good as d2u by dy dx. So left hand sides are equal, therefore the right hand side should be equal. So this implies is d2 by dx squared plus d2 by dy squared of u is equal to of v is equal to 0. Similarly, if you do the same for u, then you can get d2 by dx squared plus d2 by dy squared of u is equal to 0. So this says that, okay, you have del squared v is equal to 0 and you have del squared u is equal to 0. You came across these kind of functions time and again when you study mechanics, even thermodynamics. Del square T is equal to 0, gravitation, del square gravitational potential is equal to 0, anything. So it means that you can see, no, this is a continuity. You can see first derivative exists and the second derivative exists also. So the idea is, if the Cauchy-Riemann conditions are satisfied, then the functions will satisfy the Laplace equation. It has a huge implication in physics, whenever you came across these kind of things. So now I have to specify the domain or the range which you said, please.
It also looks very similar to the exactness condition. But for the real part, so
U and V are real. U and V are real. They are not complex.
these random conditions looks very similar to the exactness condition. So can we say that it is more general?
Bole. Parvez sab perhaps can comment on that. I want to turn it off. No, you can comment on that, please.
So can we say that this is a more general form of exactness when we have the complex?
What do you mean by exactness? This is a condition for any function to be analytic. Exactness mean I don't know.
सर एक्जैक्टनेस जो होती है वो बिल्कुल सिमिलर होती है कंडीशन जो हमारे पास डिफरेंशियल
Okay. जी.
सर जो हमारे पास डिफरेंशियल इक्वेशन की एग्जैक्टनेस को चेक करने का
Okay.
कंडीशन होती है वो
Okay,
इसी
right.
तरीके की।
Okay. Right. Parvez sab, your comments. No comments. Okay. So yes, you can. But I don't want to go into that details of differential equations. But my condition is this: these are the conditions for any function if that hold that is an analytic function. If you check differential equation with this one and the exactness, you can say that okay, these are the exact. Okay. वो भी exact है. Okay. Yes.
सर जब हम थर्मोडायनेमिक में वो मैक्सवेल इक्वेशन करते हैं तो वो भी इसी तरह की चीज होती है मतलब एनालिटिक फंक्शन होते हैं
exactly. But that is this exactly they are not complex. Maxwell's
मैक्सवेल रिलेशन इन थर्मोडायनेमिक वही
no that has nothing to do. Not if you talk about the Maxwell's equation, then you can say okay, we have E is equal to grad V, right, with a negative sign. If you take a del again, del dot E, if there is no source, then del squared V is equal to 0, the potential. That's a Laplace equation. This is a Laplace equation for U and V.
For the exact differential equations, this is not even the condition. The mixed partial derivatives of the same function f that depends on two variables should be the same so that we can use a method for solving the exact differential equations. So because of the mixed partial derivatives, it looks similar,
like that,
but it's like not even similar to
That's
this.
why I'm buying only these relations. This is the implication of that relation, that you have a harmonic functions, you call them the harmonic functions. So my whole idea was that suppose U is some function that is well defined in some domain, V is some function that is well defined in some other domain. My only worry is that is there any place where U and V, the combination U plus iota V is analytic? Yes, only in that part where the two domains intersect each other. So if I say that okay, U is well defined over here, V is well defined over here, then both U plus iota V is well defined over here. And that's why you say that okay, these are the harmonic conjugate of each other. You remember the harmonic conjugate? Why? Because U is related to V, V is related to U. Then you call them as a harmonic conjugate. I used to remember them like though they are not harmonic conjugate, but the conjugate variables in the classical mechanics. That if there is a cyclic coordinate, then corresponding generalized momentum is constant. So they are conjugate, So here, let me clarify this point slightly more. If you give me U, I can find V with the help of the Cauchy-Riemann conditions. And it means then I can find a combination of U plus iota V, which is analytic, because it came from the harmonic equation, from the Cauchy-Riemann conditions. Let's try it for a very simple case. Let me justify my claim with a very simple example. So till now the crux is Cauchy-Riemann conditions ensures the functions to be analytic. Rest was just mathematics. So if I have u to be in any rectangular coordinate is kind of an area, x and y. Can you calculate v? Anyone? This is harmonic function, by the way. This is harmonic function, isn't it? Of course, you have a linear bar of x. If you take two derivatives with respect to x, of course that is 0. So this is harmonic function. Let me find out the harmonic conjugate v. Any help to find that? You know Cauchy-Riemann condition. du by dx is dv by dy. So what is du by dx? I have to find v. So my du by dx is what? Y. So it means I have a dv by dy is equal to y. Can you find v then? So it means I can, and remember v is a function of x and y, and so is the u, which is a function of x and y. So you can say, okay, anything which v is, okay, this is y squared over 2 plus any constant in x, because it won't change anything. If you take del squared, there's no problem. You can take it even 0, there is no problem at all. So you found v. Anything else that you can do? You could, okay, do it then. Tell me what will be the result, okay? Then, what is dv by dx then? Okay, dv by dx is equal to what? Okay, this is h prime of x. Derivative of x with respect, derivative of h with respect to x. So this is equal to what? This is, which is equal to minus x. So you have h prime of x is equal to x. So only one x satisfies this one, only one relation satisfies this, that is x squared. So this implies then my h of x is minus x squared over 2, right? Because if I take the derivative, I get x. Now you have everything, right? You have everything. You have v now. What is v? V is minus x squared over 2 plus y squared over 2. Again, the rectangular coordinates. Can you check if this is analytic function? You can always, okay, so perfect, thank you. Thank you, you have a constant, exactly, thank you very much. Okay, so you can see that again you have a relation of a rectangular coordinates, minus x square plus y square. Now go home and do and check f of z, which is u plus iota v. You know u, you know v, you know Cauchy-Riemann conditions, and check if this is an analytic function or not. Can you do it very, very quickly? I can do it. F of z is equal to xy minus x squared minus y squared. You can take constant to be c, there is no problem. It's fine, right? Over 2. Oh, sorry, you are right, man. Thank you, thank you. Okay, u plus iota v. Okay, this one, right. So you can take iota to be common, right? And you have a negative sign with here. And then you take minus iota to be common, then you have, so this is minus iota, you can take common, and then you can write it as z squared over 2 plus c, right? Because z squared becomes x squared minus y squared plus 2xy. It's fine. You see, it is a function of z only. It has no z star. So it means partial f over partial z star is 0. Therefore, it is an analytic function. So you can see, from analytic conditions, from Cauchy-Riemann conditions, using those conditions, given u, you found v, right? From that v, you have found a function f of z, and you have checked that, okay, that function is analytic function because it has to be analytic because V came from U, right, from the Cauchy-Riemann conditions. And this way of finding U and V from each other is known as a harmonic conjugate of each other. In this way, you can find any pair. For example, I give you V, you can find U. And if whatever you will find from that V, if the derivatives exist, everything, and the Cauchy-Riemann conditions are satisfied, the final outcome of the function is always an analytic function.
I have a comment on this condition, this partial Cauchy-Riemann stuff. I think it's necessary, but may not be
Sufficient, yes.
You can make f of z that have poles at some z naught.
I'm not, okay, yeah, I'm not talking about the poles, you know.
Since z and z star are independent, any
Exactly.
function of fz will have this
Exactly.
equal to 0.
Exactly.
But a general function of fz can have poles, and still its derivative is 0.
So
So
I will
I
come
think-
to this point,
yeah.
that poles. You know, then I have to eliminate those portions in order to have an analytic function. My functions will be analytic everywhere except at that point.
Okay.
So as I haven't talked about the pole is reserved for the next lecture, so that's why I haven't.
So there's one more thing. Since z and z star are independent, so this condition looks quite trivial then.
Exactly,
I mean,
exactly. You know,
I mean,
when
it should not have any non-zero derivative if it's
Exactly.
a function of z.
Exactly. But I said that instead of checking Cauchy-Riemann conditions all the time,
Yeah.
you can just check if your function involves z star, you can say that, okay, it is not an analytic function.
Yeah, for
So this is a
non-analytic, yeah.
mathematical triviality, simplicity, you know.
Yeah, yeah.
And this ensures that z and z star are independent because it's a partial derivative, explicit derivative.
Thank you.
Yes, Ahmed.
Sir, what do you mean when you say z and z star are independent, like linearly independent?
They are really a function of x plus y, iota y and x minus iota y.
अच्छा
क्यों complicate करना है जिंदगी को इतना? Yes. So I have to derive one last thing. I'm not sure if I have to.
Sir,
Yes, please.
so what Nishad was saying was actually kind of right.
Right, okay.
U and V, which are real functions of x and y, when we put them with an iota and then we make a w or a complex function, then do they become complex? So U and V separately have to be exact. So the condition for checking exactness is that their mixed partial derivatives
Is vanished.
should be equal. So we use that.
That condition,
So
yes.
it means that U and V are separately exact differentials. So
Right.
I'm just correcting myself.
Sir, I think that this is the more general form of checking exactness in differential equation because we have complex number here. So
Okay.
yeah.
Thank you.
I'm not sure if it is saying that f of z would be exact though, because
No, I'm not
it-
saying anything.
Yeah,
Like that, but because my whole
mean,
worry is this analytic
yeah.
function. Because you will see in next lecture, f of z is very. By the way, one thing you are ignoring, you know, and that is if you have some function in in terms of a real variable. Perhaps I'll come to this in next lecture because I have to do one more thing in this lecture. And if first derivative exists, it never ensures that the second derivative will exist also. If second derivative exists, it never ensures that the third derivative will exist. But here it is not. If f of z is analytic, all its derivative will be analytic too. It means I can write a Taylor series for that unless and until I do not have any pole. Because if I have any pole, then I have to write a separate series because z to the power n for any polynomial with non-negative n is analytic, but 1 over z, which is a rational fraction, is not analytic at z is equal to 0. So I have to specify the nature of a pole that is kind of a simple pole, order of a pole, etc., etc. This will be covered when we talk about the Lorentz series. But whenever we write a series, we have to ensure that that series is convergent. And we have to specify if that series is convergent, what is the region or domain of a convergent of that series. This is exactly the question which Ahmed asked me at the start. This I'll come in my next lecture, okay, that suppose some series is convergent, what is the range or the, you can say, domain of that series to be convergent. And there are the simple tests, but I will use only one of the tests, you know. So this I'll come to it later, you know.
Just a small comment.
Yes, please, sir.
One of the most amazing things about complex variables is the following. I have the complex plane. Suppose I have three singularities, three poles. Other than those three poles, I know the function everywhere if I know it on just a small interval.
Yes.
So suppose I know the function exactly on a tiny strip, the tiniest strip that you can have, then I know it everywhere.
Absolutely.
How?
This will show.
How? Because you can write the Taylor series to an infinite order, and all those derivatives exist.
Exactly.
If I know the function exactly, I can evaluate all those derivatives at one point. That's the intuitive way of looking.
Yeah, you know, you remember in differential geometry lectures, you wrote that this Taylor series, you know. You have considered only the first term, you can consider second term. It means you have some coefficient of the series, you can take it as an an, and then there is no condition and you can take n from 0 to infinity, there is no problem at all. So you can write, you have to subtract that point where you have a small pole or singularity. So you can expand that series around that point, and then you can write this thing in terms of the derivatives. Exactly. And analytic continuation is slightly different concept. For example, okay, so suppose you have 1 over z minus 1. It is not analytic at z is equal to 1. But you can always change it, you know, you can change, you can write minus 1 as 3 by 2, for example, 1 minus 1 plus 1 by 2. It is again, you can write it like this one, minus 3 by 2 plus half. So you have changed it, you have make a circle bigger, but that is continuous everywhere, but still it is not well defined at z is equal to 1, because you have just rewritten it in terms of some other way. So this is kind of an analytic continuation, the intuitive way of analytic continuation. We'll try to understand in a very, very simple way in next lecture, okay? I'm just gathering the questions for the next lecture, and I'll try to answer all those, you know. This you can say that the analytic continuation, because previously the function was not well defined at z is equal to 1. No, still not z is equal to 1, but it is well defined on a radius which is much bigger than 1, except at z is equal to 1. Right, so this will come to this point in next lecture. So I think now the time is short. So what I'll do in next lecture, I'll do this in polar coordinates and prove that my this df by dz is independent of. So let me write, if I write f is equal to, let's say, r e to the power iota theta. Instead of r, let's write r naught. And if I calculate df by dz and use my Cauchy-Riemann conditions, you know, and I say that, okay, it is independent of this theta, because on a radius, on a circle of a fixed radii, only thing that you can change is theta, because here, suppose you have suppose you have some point z here, you have z plus delta z here. So what is delta z then? Delta z is x plus iota y, and you know that this is r naught e to the power iota theta, right? I can calculate it from this one. I can write delta x plus iota delta y, and then I can write delta x as r naught cos theta and delta y as, so I can write delta x as r naught cos theta, delta y as r naught sin theta. I can use it in terms of delta x and delta y. See if I can take common out, if I have suppose I have some kind of vector iota theta outside, and from these conditions, if I have iota theta, this will go to 1, and it means it has no dependence if you change z on this circle of fixed radius. It means now your derivative is perfectly continuous, there is no problem. So this I'll do in next lecture. Explicitly I'll prove it. Right, so up to the constant there is no problem. You will see that this phase factor will cancel. So this is the content for the. I'll start with this from the next lecture. So let me summarize what I said in 1 minute. Today we have studied that. My claim in yesterday's lecture was that f of z and f z star, they are the functions of different combinations of x and y. So for a particular combination of x and y, which is x plus iota y, if the derivative of the function has to exist, then the mapped functions u and v from z to w plane, which we got, they have to be, their partial derivative should exist. Not only partial derivatives should exist, they should be continuous, because you have seen that del squared u and del squared v came to be 0, but after applying the conditions of Cauchy-Riemann conditions. So if these three conditions hold, then that function is an analytic function. What I haven't done today is the range of the analyticity of any function. For example, you have exponential function. I haven't talked about the entire function. That is still remaining. So I'll talk about the entire function in next lecture. In principle, I have to talk today, but in next lecture I'll talk about the entire function. So if function is analytic in some region, and as previous of that, if it's analytic in whole z plane for z less than infinity, then such kind of a function is an entire function. And you will see that sine, cosine, exponential, their combinations, they are all entire function. So this I'll do in next lecture. So thank you very much. It's time up, so please, but you can ask questions. Jazar Sazaka.